Hello, in this chapter we are going to discuss electrical flux, Gauss theorem and its applications. First, electrical flux. Electrical flux are the electrical lines of force. Number of lines of force are more, means electrical flux is more, and vice versa. Flux density, E, electrical field is also called flux density. Number of lines of force, flux upon area of cross section. So flux is E dot A. E means electrical field, A means area of cross section, sometimes S stands for surface area. Dot product, so ES cos theta, this is the equation here. If theta is equal to 0 degree, means area normal, unit vector and electrical field they are parallel. So theta 0, phi is equal to ES cos 0 means plus 1, that is called positive flux. Means lines of force are coming out of the surface, or it is exiting or emitting, called positive flux. If theta 180 degree means electrical field and normal unit vector to the area surface, its angle is 180, cos 180 is minus 1. So this flux is called negative flux. It means number of lines of force are going into the surface, linking the surface or entering the surface. Normally perpendicularly, this is the negative flux. The difference between positive flux and the negative flux, if the lines of force are coming out of the surface, it is positive flux. Going into the surface, it is negative flux. Suppose theta 90 degree, it means electrical field normal unit vector to the surface, these are perpendicular, angle 90 degree, cos 90 0, so there is no flux linkage with the surface. Now Gauss theorem. Here Gauss theorem, as per the Gauss theorem, Gauss law, flux linkage is directly proportional to the total charge enclosed, or 1 upon epsilon naught times the total charge enclosed. Mathematically, flux can be written as integration for the closed path E dot ds is equal to q upon epsilon naught, where q is the total charge enclosed the closed surface. Proof of this is, say, suppose we consider here at the center positive q charge. We imagine a Gaussian surface, closed surface of radius r here. As it is positive charge, electrical field is coming out, and this area of cross section, imaginary small area, can be written as ds is equal to area ds into normal unit vector. An electrical field vector can be written as E r cap. Angle between r cap and n cap is 0 degree. So r dot n cap is 1 into 1 into cos 0 is 1. Normal unit vector and radial vector both are unit vectors, so 1 1. So r dot n r cap and cap dot product is 1. Now taking just to prove it, taking the left hand side of the Gauss theorem, here LHS integration for the closed path dot product, so E ds cos 0, E means electrical field 1 upon 4 pi epsilon naught q upon r square, and ds cos 0 1. So this is the closed surface of the area for sphere. Area of the sphere is 4 pi r square. 4 pi r square cancel out, so remaining here is q upon epsilon naught, which is RSS. This way Gauss theorem is proved here. It is true for any closed surface, whether it is spherical or any hodgepodge or zigzag, any, but it must be closed. But it is not a closed, Gauss theorem cannot be applied. Now we can derive here Coulomb's law using Gauss theorem. Is very simple, just reverse में लिखना. So let us consider here this is the charge q at a radius r. This electrical field outward because of positive charge away from this positive charge. And let here on the surface at a distance of r, we put here test charge q naught. Using the Gauss law, Gauss theorem, integration for the closed path E dot ds equal to q upon epsilon naught. E, because we have to find out the value of E here, so we will not put the value of E, but we are proving or deriving the Coulomb's law. So we cannot use here E, the value of E. So E is taken out. Phi, integration for the closed path, the angle between E and ds, normal unit vector, that is say 1. So integration for this ds area for spherical surface, area here is 4 pi r square. This way you can find out the electrical field value 1 upon 4 pi epsilon naught q upon r square given by equation 1. If we put the trace charge q naught here, the force on q naught will be q naught E. Putting the value of E from equation 1 here, we get the equation 2, which is the Coulomb's law. It is very simple to derive the Coulomb's law from the Gauss law. Suppose here, if dipole is enclosed negative and positive charge, to in totality it is 0. So net charge is 0, flux is. We are discussing the applications of Gauss law. First law, to find the electrical field due to the line charge. Means this is the line charge here. If positive charge is there, electrical field is away from this line charge. If it is negative, then electrical field direction is towards this negative line charge. Again, we are writing the Gauss theorem. Integration for the closed path E dot ds is equal to q upon epsilon naught. Q must be enclosed. Here we are defining the linear charge density lambda equal to q upon L. So q is equal to lambda into L. L is the length of this line charge conductor. Here for the closed path, we are dividing into 3 parts: surface area 1, surface area 2 and surface area 3. For these 3 areas, we are integrating this E dot ds for area number 1, for number 2, for number 3. It combinedly तीनों का मिला के क्लोज सरफेस हो गया. तो Q की जगह हमने क्या लिखा है यहाँ से, lambda L upon epsilon naught. For first surface, electrical field and the normal in vector angle is 90 degree. For the second surface also, it is 90 degree. Cos 90 will be 0, we know. So for first part and second part it will be 0. But for third part, r cap, n cap, they are parallel. So angle here is 0 degree or r cap, n cap is 1, we know. E, we have to find ds. इसका area क्या होगा? Curved surface area for cylinder is 2 pi rl. ये 1 हो गया. So L cancel out here. So this electrical field here is lambda upon 2 pi epsilon naught r. Here everything is constant, so it is inversely proportional to r. This is the graph here, E inversely proportional to r. So this is the graph. Direction of electrical field away from positive charge, line charge, and if it is negative charge, direction of electrical field towards the line charge. Now the second application. Find the electrical field inside, outside and on the surface of the charged spherical cell. We know spherical cell is the hollow sphere with thickness is almost negligible, very less. This is called spherical cell. So all the charge is on the surface only. There is no charge inside the hollow sphere or spherical cell. So inside there is no charge. There must not be any electrical field. So we have to find the electrical field at point P1 inside point, at point P2 on the surface, at point P3 which is outside the spherical cell. We are going to find out the electrical field at point P1 inside point where small r, that is variable radius, is less than capital R. Capital R is the radius of the spherical cell. So inside Gaussian surface, radius is small r is less than the capital R. As there is no charge inside, no charge enclosed inside, the electrical field must be 0. By Gauss theorem also, Q is 0, so electrical field must be 0 given by equation 1. At outside point P3, where small r, variable radius is more than radius of spherical cell, so using Gauss theorem, E निकलना है हमको and ds r cap n cap 1 2. So E will be, area हो जाएगा 4 pi r square equal to q upon epsilon naught. E outside equal to 1 upon 4 pi epsilon naught q upon r square. For outside point, this spherical cell behaves like a point charge. So E outside inversely proportional to 1 upon r square. At point P2 on the surface, just replace small r with capital R. This value is maximum. The graph between, say, electrical field and the distance from the center R, as we have seen here, inside point there is no electrical field, that is 0, given by equation 1. And on the surface is maximum. Outside is inversely proportional to R square, so the electrical field outside it is decreasing like this. So this is the graph between electrical field and distance R from the center. Now another case, to find the electrical field inside, outside and on the surface of non-conducting uniformly charged distribution for solid sphere. Uniformly charged distribution distribution. This distribution here is uniformly charged distribution. Uniformly means if say density is the volume charge density rho, volume charge density is given as charge upon volume, q upon volume here of the sphere. At point T1, inside point where small r is less than capital R. Small r is less than capital R means inside point. At point inside P1 here is the inside point. Small r is less than capital R. This is the variable radius. This is the radius. Capital R is radius of the sphere, non-conducting solid sphere. So inside point here, there must be some charge. You can find out the charge, effective charge inside by the unity method. So using the Gauss theorem, integration for the closed path E dot ds equal to q effective upon epsilon. We are talking about the inside sphere, that is medium here, no vacuum. So we are writing here epsilon. Epsilon is the permittivity of the medium. Epsilon not नहीं लेंगे क्योंकि medium है. And q effective can find say inside if total volume here is 2 4 pi 3 pi r cube, then the total charge enclosed is q. It is given in question or total charge on the sphere is q. If unit charge 1, then it is q upon this 4 by 3 pi r cube. This is also called charge upon volume, is volume charge density rho. For a smaller volume 4 by 3 pi r small q, small r is inside radius. So q effective will be density multiplied by the volume given by equation 2. This is the effective charge inside the smaller sphere of radius r. They put it here in the equation 1, Gauss theorem. Here E dot ds equal to q effective will be this rho volume charge density multiplied by this volume inside and ds r cap and cap 1 in this. So we know the per sphere, this is the surface area 4 pi r square equal to, so 4 pi r square can be cancelled out like this, remaining here is r. E inside will be rho upon 3 epsilon r. Inside point के लिए this is directly proportional to r. Or inside point, if from the center up to the surface, this is directly proportional, so increasing. You can see the graph. Now from outside point, for outside point at P3 r is greater than r, using the Gauss law, E dot ds integration r cap and cap 1 equal to q upon epsilon naught. This is the area. So E outside will be 1 upon 4 pi epsilon naught q upon 4 pi r square. So we can write here like this. E outside will be 1 upon 4 pi epsilon naught q upon r square, which constant 4 pi epsilon naught constant. So E outside will be directly proportional to 1 upon r square or inversely proportional to r square. At point P2 on the surface r is equal to r, we are replacing the small r with capital R. This is the maximum value. Now we have plotted the graph for inside point. It is electrical field inside is directly proportional to r. At the surface this is the maximum value, and after this it is decreasing as E outside is inversely proportional to r square. This is the graph between electrical field and distance from the center. Now the next case here, to find out the electrical field is the last application. To find the electrical field due to the infinitely large charge sheet, in the Gauss theorem, electrical flux equal to integration for the closed path E dot ds equal to upon epsilon naught. Here this is the surface charge density like so. Here positive charge means electrical field must be away from this both sides. We are considering here P point and P dash point. This is the disk. If we magnify it, it will behave like say small cylinder. So at point P, electrical field is away because of positive. At point P dash also towards right, it's again away from the sheet. Using the Gauss theorem, integration for the closed path E dot ds or dA at point P at point P dash. This is total charge Q upon epsilon naught. Two charge can be found by this 2 equal to sigma into A. This is surface charge density, charge upon area. So sigma is surface charge density, A is the total area. N cap normal unit vector. For positive charge sheet away from this, and for negative charge it is towards the sheet or inward. Here E area, total area cos 0. Here also for P dash point, E and area normal unit vector same direction, so cos 0. Here also cos 0 for this P point, here also cos 0 for P dash point. So EA cos 0, EA cos 0, cos 0 cos 0 1, EA plus EA is 2EA equal to Q equal to sigma A. Now A and A cancel out. Electrical field is given by sigma upon 2 epsilon naught. In vector form, electrical field vector is sigma upon 2 epsilon naught. N cap is normal in vector, positive, away, negative, and as we see from the formula, electrical field here is does not depend on distance. So graph between E and R, distance R is the distance, it is a constant quantity. No variation because electrical field is not depending on distance. We are considering here a thick sheet. Both sides charges are there. So electrical field is given for thick sheet. This for thin sheet, and for thick sheet it will be double, so we can find out the upon epsilon naught. This is the electrical field formula for thick sheet. If it is a conductor, charge resides on the outer surfaces, so there are two surfaces. It means the same formula is valid for conducting or conductor or conducting part. So it's very important point. For thick sheet and for conductor, we are getting the electrical field given by sigma upon epsilon. Sigma is the surface charge density. For thick sheet is double than the thin sheet.